Assalamualaikum and a very good morning to everyone. So this class will start with the third video uploaded in YouTube, and this is the beginning of the asynchronous learning as compared to the last few classes we did. Asynchronous learning for me, okay, means that I'm going to upload YouTube videos for a certain length, and it's usually around 15 to 25 minutes, and then I will put like a gap in the terms of activities, okay, such as peer instruction, and then we have Kogel. So what is Kogel? Later I will explain, and then I will have some other activities related with journal articles. Okay, so this is still introduction of spectroscopy methods. Okay, in the first few slides of my first class, okay, I show you this photo. This photo is where to show you how the atmosphere in the outer layer of our Earth is acting as the filtering media for sun radiation. Okay, sun radiation is a white light. It's a very high energy white light. But when it arrives towards the atmosphere of the Earth, the atmosphere of the Earth filter, okay, when I said filter means that it absorbs certain amount of radiation that is harmful to the Earth, and it transmit out the light that is enough for the usage of the mankind. Okay, so recap your basic science back in the secondary school. Your basic science says that atmosphere contain certain percentage of nitrogen, being the biggest major gaseous element in the atmosphere, and then we have oxygen, and then we have certain percentage of noble gases. Okay, so what is the relationship between what I explained to you about this atmosphere of radiation? So you have to think about how I said before, we manipulate radiation, okay, from a certain source, okay, and then we bombard it into our sample, and then when the sample absorbs certain amount of energy, it will transmit what's left. Okay, in instrumental analysis, we have certain parts, certain mechanical instrument inside our instrument that can act as the filter, as the detector, and so on. Okay, so in this case, okay, in this photo over here, so you imagine that the sun is here, and then it will bombard all the radiation that is very high energy, and then it will go towards the apa ni atmosphere at certain wavelength. Okay, we talk about wavelength as well before. When higher energy means that the wavelength will be smaller. Okay, as indicated by this ultraviolet over here, you see that the wavelength is smaller as compared to the infrared. Okay, so when atmosphere filter out this one, it will only, for example UV, it will go towards the Earth only UVA, while UVB and UVC will be filtered out by the atmosphere. So relate all this kuasa Tuhan, okay, relate all this the God creation into the manipulation of this phenomena inside an instrument. Okay, now next slide. Okay, so in spectrometry, we will have several instrumentation that is very useful and very important for us to understand. Okay, we have, in the first place, we have source. What kind of source? Are we going to use the sun as the source? Of course not. So we find something that is similar to the sun in terms of the emission of the white light. So we have a lot of example for sources, such as we have the deuterated lamp, we have the tungsten filament bulb. So all of these can give you white light at relatively lower energy, of course. And then after you have source, okay, what to do with the source? So we want to select certain wavelength for it to bombard to our sample. So we have to have monochromator. So monochromator in my analogy in the first slide is like the atmosphere. Okay, except that monochromator in spectrophotometry consists of mechanical parts, including opticals. Okay, and then when the monochromator select what kind of wavelength of the radiation you want, it will bombard the sample. Okay, what happens in sample? It can either absorb, reflect, and then will transmit whatever left. Okay, next we have detector. Detector, what kind of detector? Is it CCD? Okay, is it apa lagi we have? PMT and so on. So this detector will detect whatever left. Okay, and then you will get your readout in terms of the PC monitor. For example over here, okay, I show you the Perkin-Elmer UV visible spectrophotometry. The size is as you used in your inorganic lab before. It is size of like computer desktop, and in Department of Chemistry, it is one of the most cheap, okay, instrument in our department. Okay, therefore you can see a lot of this UV visible spectrophotometer in our department. Okay, so this UVVs we have source. Okay, when you see the word UV and visible, means that you will have two sources. Okay, you will have two sources, whereby one source will give you radiation that will be high enough of energy until it can give you UV, and another one is relatively lower energy and can give you visible. So in this case, source for UV is deuterated lamp, while source for visible will be tungsten filament bulb. Okay, this is the beauty of UV spectrophotometer, whereby the source are two. Okay, the only instrument that can have two, okay, means that research has incorporated a lot of the opportunity to put more. You can also find UV spectrometer only, okay, and combine with visible, you have the second one lah. The monochromator comprise of entrance slit, and then we have like dispersion device prism, and then you will have exit slit. Don't worry, this is not a dedicated slide for UV, but I just want you to understand how I relate the instrumentation in spectrophotometry with the electromagnetic radiation around the Earth. Okay, and then it will bombard to the sample, and then detector will detect. Okay, so components of optical instrument, you can read this on your own. I already explained now. Done. Okay, now when you are talking about spectrophotometry, it comes hand in hand with Beer-Lambert's law. What is Beer-Lambert's law? It is simply as remembering epsilon BC. Okay, adsorbance over here, okay, is linear to the molar adsorptivity of the species inside your sample cuvette, and also linear with your path length. What is path length? And C, linear to concentration. That means the higher the adsorbance when you see the signal inside UV meter, for example, it indicates higher concentration. Is this the same like the one in chromatography? Whereby in chromatography, the statement says that the higher the peak height means that the concentration is higher as compared to those with lower peak, right? Remember in your previous class, the same thing over here, but Beer-Lambert is only applicable to certain extent. Okay, I will explain to you certain extent, what kind of certain extent later. Okay, now that is the final equation to be remembered. But how do the scientists before us get this kind of equation? Okay, go back. Adsorbents change exponentially as a function of linear change in transmittance. What is this? Okay, we change the ink first. Wait, So adsorbents. Okay, remember, you have your source over here, radiation kan? Radiation. It bombard your sample. Bombard maksudnya macam bombard apa bahasa Melayu? Allahuakbar. Dikenakan terhadap sampel Okay, and then all your sample inside here will absorb. They will absorb. Why they absorb? How they absorb? And what are the chemicals element that make them absorb? We will learn in UVVs later. It will absorb and it will give you the final transmittance. Masuk sini, transmittance tinggi means radiation tinggi, dia absorb, of course transmittance rendah kan? So that's why we have the initial incident radiation and the transmitted radiation. So whatever has been absorbed means that transmittance kurang. So that's why adsorbance changes exponentially as a function of linear change in transmittance over here. So transmittance equals to P final, ni P final ni, divide by P initial. Okay, maksudnya berapakah yang tinggal as compared to the initial? Of course kurang lah kan? Okay, so what is the relationship between this transmittance and adsorbance? We have adsorbance equals to the minus log. Okay, minus log T. Okay, kalau kita tak nak T ni, if we don't want this T, you can like rearrange the denominator and numerator. So we have a rearrangement log 10 P initial divide by P. Yang ni bukan salah tulis nota. This is simply because we reverse the negative. So dapat P initial over P final. Okay. So from here, we simplify some more. Okay. And we get A equals to epsilon path length and concentration. Sama balik yang macam ni tadi. Okay. So epsilon, what is epsilon? Means that how well the analyte can absorb a certain radiation given to it. Okay. The higher the epsilon means that it is a very good UV visible. It is a very good species that can absorb a lot of radiation. So when you want to analyze analytes, you want to see a very high epsilon so that you can get a very good absorbance. Okay. So B is path length. Path length ini lah. Okay. Apakah ini? Ini adalah QVAT. Okay. QVAT, the one that is shown inside the UV visible spectrometry just now. So this is the path length. The higher the path length means that you will have higher absorbance. Remember, ni semua linear. Therefore, you will get concentration. Okay. Okay, this is another slide showing the simple diagram of the Beer-Lambert's law. Okay, the concentration, okay, the unit will be molarity. Okay, bukan mole, bukan ppm, but molarity, mole per liter. Okay, the path length of your sample will be cm. The molar adsorptivity is a liter per mole per centimeter, and adsorbance is usually unitless. Okay, tak ada unit. Okay, we go to the next one. I put over here. Just now I already explained. Okay, now this is to show you. Okay, when you have higher adsorbance ni y-axis, wavelength sini x-axis, the higher the adsorbance, sini berapa? Oh, 6.5 for example. The higher the adsorbance means that the concentration is higher. This is in relation to the one over here. This is around 1.8. The concentration is only 633 micromolar, while this one is 3.16 millimolar. Okay, so when you do graph, you will see that the higher the molarity, the higher the adsorbance. Is it going to be linear like this forever? Of course not. It will get certain time, and it will go plateau or even go down. This is where the part we call as deviation in Beer's law, Beer-Lambert's law. Okay, ini sama tadi. Okay, so I will explain to you on how do we use this equation. Okay, for example, a sample in a 1 centimeter cell is determined to transmit 80% light. Transmit maksudnya berapa persen dah diabsorb, okay, at certain wavelength. Okay, for example 250 nanometer lah. Okay, if the adsorptivity of this substance is 2 liter per mole, ini liter besar, 2 liter per mole per cm minus, what is the concentration? So you put here, you want C, you have B over here, you have epsilon. Okay, you have epsilon over here. Okay, so it is asking you what is C. So you have to rearrange your equation lah. Okay, but you don't have adsorbent kan? You tak diberi adsorbent, but you are given transmittance. So you have another small equation, A equal to minus log T. So you incorporate T as 80 over 100, you will get adsorbance of 0.097. Tak ada unit And then once you get this, you get 0.097 equals to your epsilon times B and then times C, the one that you want. Okay, you will get 0.048 molar. 0.048 molar berapa milimolar? 1, 2, 3. So 48 millimolar. Okay, so this is 48 millimolar of substance inside the sample that is represented by the one that you put inside the 1 cm cell. Okay, so this is the deviation from law. Okay, and you have a graph. It is linear to certain, and then suddenly it will become plateau and then go down. Why? We have several reasons, and the most significant reason is the chemical deviation itself. Okay, we have millions of chemical compounds. Okay, not only like included inside the periodic table, but remember we have millions of organic compounds as well. Why I was talking about organic compound? Because UV visible spectrometry is a molecular spectroscopy method that can detect organic compound as well. So we have to understand a lot of chemicals. Okay, so chemical deviation usually come because we are analyzing sample or analyte that is very high concentration. For example, you want to analyze I give you example of nitrophenol kan, nitrophenol. Okay, you bring into the lab sample yang ada sampai 1000 ppm. You learn before in principle of chemical analysis, you have macro analysis, you have micro analysis, and then you have trace level analysis. most of the analysis we do is in trace level or micro. So 1000 ppm is macro. Macro maksudnya terlalu pekat. Instruments available nowadays are only suitable for trace level and micro. Therefore, when you bring in 1000 ppm analyte into the UV visible and then you do your curve, you will have this kind of plateau. And ada juga sampai bawah. Okay? Why? Because of the electrostatic interaction between the analyte, the chemical compound inside the cuvette. Okay, understand? And then we have chemical reaction that is associated with the dissociation. Dia dah terlalu pekat, okay, and it can also dissociate, okay, certain level. Now we go into instrument deviation. Instrument deviation is usually comes from the the effect of polychromatic radiation. Okay, means that the radiation is not suitable for our monochromator and therefore it will not go into the slit very accurately. Dia tak pergi accurate. Mungkin dia pergi macam ni. Padahal dia punya slit mungkin dekat better dekat sini. So dia pergi sikit. Or you will have it goes into the monochromator, but once it reach ni cuvette you, and then you have detector. Once it reach the cuvette sample, dia reach detector tu dia stray. So susah lah. Detector nak detect mana? Ni ke, ni ke, ni ke. So the scattering happen inside instrument as well. So when this happen, usually it can be overcome by manipulating the parts only. Okay, chemical deviation you can manipulate by diluting. You can dilute lah. Dulu ada buat analisis ataupun this semester we will see analysis whereby you bring a concentrated sample and then you go to the lab technician, he says this is very pekat lah, you have to dilute. Why? Because he's talking about the deviation you will see later. Means that when you do graph, you will not get R square near to 0.999. Dia takkan dapat because of this problem. Okay. Okay, last example. This is my few of the slides, last slides. How, okay, a 1 gram tablet, 1 gram tablet containing drug D, having this kind of molecular weight, has a molar absorptivity epsilon of 703. And then if you dissolve in 1 liter water, and then you get adsorbance of 0.687 in a 1 cm cell. Okay, when you see the word 1 cm cell, you know already this is UV visible. Okay, what is the percent weight of the drug in the tablet? So this is the combination of calculation using C and also weight over weight percent yang you belajar dulu masa like chemistry, chemical analysis principle. Okay, you calculate berapa tadi concentration guna ni. Dia dapat 9.77 times to 10 to the power of minus 4 molar. Okay, and then you want to know how much is it in gram. You dah dapat concentration, then times by the molecular weight times by the 1.5 liter, you will get this amount. And then divide, don't forget about the 1 gram tablet. So bayangkanlah D ni ialah paracetamol. So we have 39.6 of paracetamol in the 1 gram tablet. Okay. Okay. Now we finish the third part of introduction of spectroscopy, and we will now resume. Okay, we will now do the active learning. Okay, of doing the refreshing on how to do linear calibration curve. Okay, team A is the one having even number, and team B will be odd number. Team A means you kena check you punya list nama. Even number, team B is odd number. Okay, so team A, what you have to do is that you have to do what's this question? Okay, team A, construct an external calibration graph. Okay, what is external? I hope you still remember. Find the concentration of zinc inside A. So I already give you sample A is like this. Okay, you have to do curve based on this data, and imagine that is you are analyzing it using AAS. And then team B, you have a 5 manganese standard solution containing real wastewater. So when the word real wastewater comes in, means that you can imagine that is going to be a standard addition graph. So team B construct a standard addition graph out of this data, and you have to find out how much is X. X ni manganese tu Okay, one lucky student will teach audience from team A of the finding. This one only lah. Nanti I panggil lah siapa-siapa. Yang ni from my previous notes from previous classes. Okay, so we spend around 15 minutes, and then you can okay, I will ask you on how to share your graph later. Maybe we upload in e-learning or what. Okay.